Swayam Prabha. Digital India. Educated India.
Okay, so in this lecture I will be talking about cellulose and how we can use cellulose to make various products. If you recollect from the previous class, we were talking about sugarcane bagasse, from which cellulose was derived, and then how it was used for various disposable containers, right? So cellulose is most abundantly available in many of the agriculture waste, and after sugarcane bagasse, the next thing is rice straw, rice husk are also very rich in cellulose. So rice is the third largest crops in the world after corn and sugar, and in 2023 about 800 million tons of rice or paddy was produced, and this rice husk is an important agriculture waste. Okay, so usually how we manage at this point is we either use them as a waste to energy, we burn them for energy, or sometimes we use them as a filler for biocomposites. We can also use it for extracting silica from rice straw. Okay, these are conventional applications. And if you look at the chemical composition of rice husk, roughly about 33% is cellulose, 26% is about hemicellulose, and there is about 7% lignin. What would you say about the amount of cellulose present in the rice versus bagasse, sugarcane bagasse? Where is it more? Sugarcane bagasse had more, I think about 40 or 43% roughly. Okay, the next highest is in rice husk. Okay, so what's the difference between cellulose and hemicellulose? So cellulose is made up of repeated glucose units, linear, crystalline. Hemicellulose on the other hand would have many other sugar units, xylose, galactose, glucose, and it's amorphous, branched, right? So when you change the molecular structure and molecular composition, the property also going to change. Of course, lignin consists of phenolic compounds, aromatics, aromatic alcohols. Okay, so here I am showing a process with which we can extract cellulose from rice husk. Pretty much the same process is used for any other agriculture waste from which you want to extract cellulose. Okay, usually we start with what is called this alkali treatment. Okay, so here I am taking the reference from this particular paper. So you grind the rice husk into powder, okay, and then treat with 4 weight percentage of NaOH under reflux conditions. Okay, why we do that? We do that because this particular alkali treatment removes hemicellulose and silica from the rice husk. And why we want to grind them into powder? There is more surface area per unit volume, so the reaction can get completed, so you have better conversion or better removal of hemicellulose and lignin. So this is followed by a bleaching process. For the bleaching process, sodium chlorate is used, and reflux conditions about 100 to 130 degrees Celsius. In this process, the remaining hemicellulose and lignin will be removed during the bleaching process. Okay. Subsequently, there is also an acid treatment, usually with sulfuric acid. One can also use other acids, nitric acid and other things. But this is at a slightly milder condition, like 50 degrees Celsius and about 40 minutes of stirring. Okay. So when you take your agriculture waste, rice straw, through alkali, bleaching and acid hydrolysis, you are basically removing hemicellulose, lignin, silica, all that is removed. So you will be left with only cellulose pulp, right? So here again from this paper I have given some composition. The untreated one has about 35% cellulose, 33% semicellulose, about 23% lignin, remaining 9% is silica. This is a raw rice husk. Once you do this alkali treatment, you can see that hemicellulose has come down and silica also has come down. Okay. but the lignin concentration is not very much affected by alkali. Okay, that's why you do the bleaching process. Okay, during the bleaching process, the lignin also becomes less, hemicellulose also becomes less. Okay, and you can see the bleached one, the bleached compound would have about 95 to 96% pure cellulose pulp. Okay, so even though this is meant for rice husk purification, pretty much any other agriculture source that you want to, suppose if you want to extract cellulose from wood, okay, or from sugarcane bagasse, or from any other fibers, you would pretty much do this. Okay, there may be a small variation in the optimization of the temperature, concentration of the alkali and bleaching agent, but pretty much the process is this. So this is how it looks like. So the untreated one looks kind of brownish thing, and then once you treat alkali, you see that it becomes little darker because the hemicellulose is gone, the lignin content is still there, and then once you bleach it, then you see this nearly white color pulp. Okay, so this white color is an indication that almost pure cellulose material you got. Okay, if this color you didn't get it, it means the lignin is not completely separated. So you may want to do this bleaching over and over few times. Okay, so the alkali treatment, bleaching treatment are typically repeated 3 to 4 times to ensure good removal or proper removal of the hemicellulose, lignin and so on. So this paper also showed some nice microstructure to see what microstructure change happens when you go through these processes. So if you see this untreated sample, which basically contains everything, cellulose, hemicellulose, lignin, you see these thick fibers, okay, representing the cellulosic fiber together with hemicellulose, pectin, wax, lignin and so on. So when you treat with alkali, you remove the wax, the hemicellulose and some fraction of pectin, which is also a biopolymer. Then you see a kind of roughness in the fiber, okay, because you have removed your hemicellulose. Okay, once you bleach it, you see this the whatever this holding together, the fibers are held together with the lignin. So once the lignin is removed by bleaching process, you see that all the fibers are now disentangled, and individual fiber can be seen. Okay, so individual fibers are now separated, and this diagram shows the diameter and aspect ratio of the fibers of the final bleached sample. You can see that this is a distribution. If you look at the white data here, the bar chart, that basically says what is the fraction of fibers in a given length. Okay, so they are pretty much distributed about 15 to 20 nanometer or 10 to 50 nanometer. These are diameter of the fibers. Okay, L by D is the aspect ratio, length divided by the diameter. That is, those are given by this filled bar chart. So you go roughly about 30 to 40 aspect ratio. Okay, the length of the fiber is 30 to 40 times more than the thickness of the fiber. Okay, and the thickness is roughly about 10 to 20 nanometer. Okay, so that means what we are saying is, if I look at this particular sample, this sample basically consists of fibrous material with the diameter in the range of 10 to 20 nanometer, and the length will be about 30 to 40 times that diameter. Okay, so you can also do other XRD to study the crystalline behavior of the material. So here, when you go from bottom to top, you are going from untreated to alkali treated to bleached to final the cellulose nanocrystal. You can see this appearance of the second peak and more pronounced peaks, illustrating that the more pure cellulose you have, more crystallinity you have. Okay, so you can see that the numbers are also calculated based on the process. So you basically go from 46.8 to 59% crystallinity when you go from a raw rice husk to cellulosic materials. This one tells you about the thermogravitic analysis. It tells you how thermally stable this material is and what are the components that are there. You see there is a small dip here. What does it signify? In all the samples, raw, alkali, bleached, all of them have small dip in the beginning. What could that be? Usually this is moisture. Okay, so cellulosic materials are very hygroscopic, they always absorb moisture. So the initial drop is removal of moisture, and then pretty much all of them have a deep decrease in about 400 degrees Celsius. Okay, beyond this material will degrade. Okay, so this kind of TG analysis will tell you what is the operating temperature you should manage this product without any degradation. So you can do all this nice characterization, and finally, okay, you have processed this pulp. We also looked at its microstructure, crystallinity, thermal behavior also. So what do we do with this? How can we make into a product? Okay, still this is a raw material. Okay, so how do we convert this into a product? So that basically takes us to several possible processing approaches that is illustrated here, and I will take you through one by one. So what we are talking about in this picture, you start with the raw material, that is cellulose, and this cellulose, I'm going to talk about two process. One is called this wet process, and there is a dry process. Okay, and by both of these we can actually make products that look like any of these. Okay, the cellulose that we obtain from this various process can be subjected to various process, wet process and dry process, and then you can convert into something that is a usable product. Okay, it's completely cellulosic. Okay, so if I take the first one is the wet molding. We call something called thick wall containers. Typically the eggshell that you see when you go to the grocery market, you see it's actually a pulp made, very rough, very thick box that you see, that is made up of this wet molding. Okay, so the way it works is you start with an aqueous suspension of your pulp. Okay, you take your cellulose and you basically dissolve it in water. Okay, so then what you need is something called a mold, and this mold here, what is shown here is a fine mesh, steel mesh containing a shape that you want to mold into. Okay, so you can see that there is a plunger that comes, okay, that will have this mold, and then you apply vacuum to pull, you suck vacuum, then what will happen is this fiber will start getting attached to the inner wall of this. Okay, when you try to apply vacuum, so you can see that once you apply enough vacuum, you will see a thin layer of cellulose coming on the top. So you will have this kind of a situation. Then you can release the vacuum, and this product will drop down in a conveyor belt. It will be very wet, okay, because it's soaked in water. So you have to send it through an oven drying, where all the moisture will be removed, and then finally you get your product and collect it here. Okay, it's a very simple approach. It's something you can always do it at your home also. You take your newspaper and then make it into smaller piece, and then you put it in water and keep stirring over and over. You will see that the pulp will become a very thick liquid. Okay, then you can take any object that you want to take as a mold, and then you can actually put a nice coat on this surface, and then you let it dry. Okay, once it dries, you can remove the mold. Then your cup, you are left with the bowl or cup and whatever that is. Okay, it's something that people do traditionally in villages, okay, of paper pulp molding. So here this is done in an industrial level, where we apply vacuum, we have a conveyor belt, we have an oven drying, little bit more systematic and industrial. So that is so just to kind of summarize what this means, we call this as a one cast or plain molding, and usually it will have two sides, the wire side and the other side. You know, when if you look at this, you see there is one side that is free, the other side is touching the mold. Since the mold has this wire frame, because of its mesh like structure, you will see one side of the product will have a mesh like structure and other will be more smoother. Okay, and typically you can achieve a thickness of between 5 to 10 millimeter, and we consider this a thick for the kind of application we are talking about. Okay. Imagine any other plastic tray or plastic material that you use. These are much more thinner, it's 1 millimeter or even lesser. Okay, but this pulp molding in this simple approach will give you something between 5 to 10 millimeter thickness. Sometimes we also see that when it dries in the oven, it can also shrink, it can also deform a little bit, so it may not keep the original shape of the mold. Okay, so that is one issue. Usually it is used for cushioning purposes. You will see in recent times you have this fridge and other white goods, when it gets packed, we no longer use thermocol. It actually comes with this pulp based molds to guard for to offer this cushioning effects. So transport of heavy products where aesthetic is not the primary target. Okay, it's a very simple process. It's not going to give a good finish, it's going to be very thick, so it's not going to be very aesthetic. So you generally don't use it for any food application or any aesthetic application. You usually use it for packaging, cushioning effect, where aesthetic is not important. Okay. Now the major issue with this approach is that there are two things. One is you're going to use a lot of water. Okay, and time to time you have to change this water, you have to treat water, and water could be a big resource. Okay. The second thing is you have to evaporate water once the mold is completed, so you have to put a lot of energy to vaporize water. Okay, so these are the two things that we have to keep in mind in this process. So this is the thick walled wet molding. The second one is called this transfer molding. Transfer molding and thick wall molding almost the same. It's just only one extra process. You see, again you start with the pulp, you have a mold, you apply vacuum, you get this, right? And then what happens is you take it to another mold. This is another mold. You bring this mold and then you actually apply a vacuum. So this mold gets transferred to here. Okay. So you see that this mold now picks up this here and then it delivers here. By doing this, now the both side would be more smoother. Okay, because you can see that here the mold, the inner side is smoother, outer side is not smoother. When it actually sucked into another mold and then you do one more vacuum application, both side of the product would have the same finish. Okay, because we are transferring this product into another mold and then applying vacuum again, and then this leads to again drying, the same process. Okay, so in this case also the thickness would be about 3 to 5. It's the only advantage of transfer molding is that the both sides will have equal surface characteristics. Okay, whereas in the thick wall molding, one side will be rough, other side will be smooth. Okay, in this case both sides will be smooth. And the third is called the thermopressing. In the thermopressing, you can see this process where we basically have a mold and then we create a layer of this pulp through vacuum, and then we close the mold, keep it over certain time for a certain temperature. Okay, so at this temperature, at this particular time, this consolidation happens. Okay, and then you can release a product from here. Okay, so here some application of pressure and temperature is allowed to densify this into this. Okay, so as you can see that so the product is dried under pressure between two hot molds, so therefore the shape is restrained. So in the previous two cases it is allowed to dry in open, so the product can actually shrink when it dries. So here you are drying while the shape is preserved. Okay, so that there is no deformation, so you will give more aesthetic look. The finished good would be very similar to the shape that you want. Okay, so typically the temperature in this thermopressing would be roughly about 150 to 200. Again, we are talking about only for cellulose. Typically pressure goes from 5 to 40 megapascal. The holding time in the mold is roughly between 10 to 30 seconds. You can go to 2 millimeter and around that to make it a stable product here. Okay, so that is, so right now we saw one is this thick wall, very simple process. Second one is a transfer molding, where you use 2 molds to transfer. And the third one is you are actually compressing at high temperature, high pressure between 2 molds, and drying happens intact, so that there is no deformation and the finishing is good. The fourth one is called processed. So in the process, what happens is basically we kind of assemble the molded parts together. Sometimes, suppose if you want to mold a bottle, you don't mold the whole bottle in one shot. You actually mold in 2 parts. You have to put it together. Okay, and if you have a clamshell kind of a box, again you do it in 2 parts, and then you have to have some way in which you can assemble them together. So assemblage and further shaping to create the final product is called processed. And sometimes we also do additional things. We add color, sometimes we print something, coat with some special suspensions and molds. Okay, so these are the typical wet molding that is out there in the industry right now. As I said before, this wet molding requires very large amount of water as well as high amount of energy to dry water, and water is something that has high latent heat, so it will take more energy to evaporate. And one of the key challenge in this process is how do we have minimal amount of material and keep the stress evenly distributed so that it will have adequate durability and functional use. Okay, if you try to decrease this amount of material, that means you are looking for a thinner one, then you have an issue of whether the stress is equally distributed or not. Okay, so those are the 2 challenges. Now, as we speak, in the last couple of years, we see a lot of new process emerging in managing cellulose. So here I have given some startups: Cellulo-Pack from Spain, Muto from Finland, Avec from France. They all have come up with some new technology which actually avoids the use of water and a lot of energy for drying. Okay, what could be the option? How can you avoid water and energy of drying and still mold? Let's first look at the website of these companies, just to get an idea of. So this Cellulo-Pack, as you can see, it has this clamshell pack, trays, and you can see that these designs are quite aesthetically pleasing, right? You see these are little thicker, and these are a little bit more finer, right? So if you go to our story, yeah, so they have a lot of things: bottles, cushions, fruit trays, cup holder. Let's look at cup holder. See, and food trays. All cellulosic. Cushions. So cushion for wine bottles, cosmetic containers, for bottles, various cups. Okay, it's a lot of products. So let's take a look at the other startups as well. Are you hungry? By looking at this, you see a very nice set of products. Very pleasing, aesthetically very pleasing. It actually looks like just like a plastic, no? So you can see how nice finish, absolutely clean and yeah, I think we have seen this before. Let's go to other one. You can see that the finish is not really good, no? Here you see it's a little rough. One side is smooth, but other side is quite rough. Look at this. Bottle holder. I don't know what they do with this. This must be what is this? What could this be? You can browse it when you have time. Okay, so these three things. Okay, so what did they do is, to avoid this water and high energy, they do what is called dry molding. Okay, so dry molding is a process which combines two well-known process, and they have combined together. One is there is a technology already that is there that actually have a methodology by which you can make non-woven fabric. Okay, so example would be this the diapers, for baby diapers that they use. It's basically a polymeric material or a fibrous material that is non-woven, just kind of gives you, water absorption and cushioning effect. Okay, and the other one is, other technologies, we know that when you heat a product and we can compress it and then give a shape to it. Now these two technologies are integrated in this cellulosic material. So what they do here is they take paper, okay, and then they shred this paper into smaller pieces. Okay, so end of the day they basically get a lot of scrap papers and pulp. Okay, now this is actually made into a kind of air-laid material, which is basically like stack of fibrous material, which is like a non-woven, unstructured. Okay, and this basically is sent through some conveyor where you can spray few things. For example, they spray starch. You can put a lamination if you want. If you want to put a plastic layer, you can put, or any other layer you can put. And finally, it goes through what is called again a compression molding. Okay, so in this case, again we are going to hold the product between two hot mold at high pressure. Okay, so at this temperature and pressure, the cellulose fiber that we started off with would actually fibrillate and become much more thicker product, and then whatever shape that mold has, that can be given. Okay, so the first thing is to make this non-woven air-laid material, and second is to put it through this thermoforming. Temperature range is between 100 to 200, pressure is between 4 to 40, and time is roughly about 1 to 3 seconds. Even though here it is shown for fluffy pulp, but you can also do the same thing with cotton, linen, other cellulosic material also. Okay, so all the product that I showed in the previous are actually done through one of these technologies. Okay, there is no water involved. Okay, it is just matter of it's a matter that you are able to make a very loose layers of paper, cellulose paper. Okay, and then you put whatever additives you want to put, and then you basically compress it, hold it there for a particular time, and give the shape. Okay, this temperature 100 to 200 degrees Celsius is the optimized temperature in which the cellulose fiber will start interacting and will form a much more thicker cross-linked polymeric network that takes the shape of the mold itself. Okay, if you do it at room temperature, this will not happen. Okay, so that will be a simple pressing, but here there is a lot of change happening in the microstructure level. The fibers will come close to each other and they intertwine and get more denser product. So as I said that sometimes they spray starch so that it is the material has adequate stretchability and processability. It is known that for paper they add alkyl ketone dimer as a chemical that reduces water uptake of papers. Okay, same chemical is applied here also, so that the product that you get is water resistant. Okay, there is no seepage and all that. Okay. Yes, there are some limitation about what's the depth of this material that you can create and all that, but I think a lot of patents are coming up, a lot of startups are coming up in this area. This seems to be the next big push in molding cellulosic material into various forms. There are few more companies, Pullpack and Yangi, Blue Ocean Closures. All of them are from Sweden. Okay, so they also have, if you go to this website, you can see that these are the nice products that they have been able to, make from dry molding. Okay, so yeah, that's all I have. I will probably ask you to go through this website and check out what products they have made, what are the technologies, and do some small activity. Yeah, just check out these websites.